Incline frame of reference and more. So what we're currently discussing is two-dimensional projectiles, right? Where the perpendicular components are independent of one another. And now that we're into two dimensions, it's a good opportunity to discuss inclines and how gravity itself was calculated by Galileo, right? Galileo calculated gravity by dropping things, right? You've heard of the story of dropping things off of the Leaning Tower of Pisa, yes? The problem with that is that he didn't have stopwatches, right? And so it would have been remarkably difficult to actually time dropping something from a height onto the ground. So what he was doing when he was up in the tower was dropping different objects, right? Lead balls that were small, large, hollow, etc., etc. And he was noticing the fact that the acceleration due to gravity was the same for all objects. But he wasn't able to actually calculate 9.8 meters per second squared through that experiment. So instead, he took a set of similar objects and set them on an incline. He knew that putting these things on an incline, they would roll down the incline due to gravity, but they wouldn't fall as fast as dropping them straight down. And so he had hoped that using geometry, he could work backwards to figure out what the vertical acceleration is. Does that make sense? And so the reality is Galileo did it backwards from the direction that we're going to do it, which is forwards, right? We're going to take what we already know as the forward acceleration or force that is down and derive it into a frame of reference that matches the incline, right? And so the incline looks like this. This angle is identified as theta. If we put an object on this incline right here, we know that based on this picture, if the ground is the ground down here, then gravity acts on this object straight down. Now, in some reference frames, this could be acceleration, as in 9.8 meters per second squared, and in some reference frames, this could be f of g, with mass times, or mass times acceleration due to gravity, or mass multiplied times g, right? Because either one of those is a vector that represents essentially the same information. Does that make sense? Okay. The problem with this particular vector is that it doesn't work with the incline, because the motion on the incline is going to be parallel to the incline, right? The velocity as this thing begins to move is going to be down the hill, v, right? Anything that is going to be independent of that velocity is going to be perpendicular to the surface, right? And so the reality is that it's much more useful to look at an incline scenario with our frame of reference rotated. We've typically done up and down, left and right. But on an incline, those directions don't really make sense because the ball doesn't go up and down, left and right. It instead goes diagonal up the hill, down the hill, and perpendicular to that would be independent, right? And so what we're going to do is we're going to take our frame of reference and redefine it so that it looks like this, where now this direction is positive x and this direction is positive y. By doing this, rotating the frame, if we know information that is parallel to the incline, then we can do all the kinematics that we've been doing, motion, acceleration, velocity, etc. You can even do momentum, collisions, and all those typical things. And if we have things that are perpendicular to the surface, then we can discount them as being independent, right? And so we can literally ignore them. However, this one vector, the only thing that is absolutely standard and exists, does not line up to these arrows, right? And so what we're going to do is we're going to do our vector resolution in order to make those things work, right? So we're going to say that any vector can be represented as the sum of two vectors drawn head to tail. And so if I think about this as being a fixed value that cannot be increased, right? Gravity is 9.8 meters per second squared. The weight of this object would be mass times that number. That is a maximum value that cannot be increased. So when I draw the triangle, that's the hypotenuse of the triangle because it has to be the largest side, right? So if I think about the frame of reference that I have, this arrow really points this direction and this direction as perpendicular components that vector add to give us the magnitude of that hypotenuse. So these are perpendicular to one another, and we would define this as our x vector, right? And we would define this as our y vector. Looking a little bit deeper, this vertical vector that we started with forms a 90-degree angle with the base of the incline, which means that this angle from here to there is 90 minus theta, based on the fact that this is a triangle, a right triangle, right? 90 degrees theta and 90 minus theta to add up to 180. Furthermore, this angle between y and the original is a complementary that is perpendicular to the surface of the incline. Therefore, this angle is theta. So you can do other geometry in order to figure out what I just said, or you can just memorize the fact that the angle of the incline is also the angle offset from the vertical at the top. If we were looking at this where the original vector that I drew is acceleration, as in g, then x is the acceleration that pulls down the hill, right? It is the component of gravity that is actually parallel to the incline, and therefore that which is accelerating the ball down the hill. So as we decrease the hill, we decrease x, and therefore slow the acceleration of the rolling object down the incline. This is exactly what Galileo did. He reduced the incline down to a reasonable amount where he could actually time in a acceptable amount of time the ball rolling down the incline, right? It took a much longer time. It accelerated at a much lower value, but that value is proportional to the theta, the angle between the surface and the horizon. So he was able to work backwards to figure out 9.8 meters per second squared vertically. Make sense? All right. Taking that same approach, if this were force instead of acceleration, going a little bit further. Oh, excuse me, I want to draw a box instead of a ball this time. If this were a box, a crate, an object that doesn't roll, right, then we are going to look at this as a force diagram because obviously it's not going to accelerate naturally because of its shape. So in this case now this becomes f of g, which like I said the top one could have been that as well, but more common for non-round objects. Given this information, right, then of course we know that f of g breaks into a perpendicular component to the surface that's here and a parallel component to the surface that's there. Oh, sorry, that should be a straight line. Being careful that these are perpendicular and f of g is the hypotenuse of this triangle, right? It's advisable to practice drawing this diagram over and over again so that you can make sure that you're drawing this triangle appropriately. This line should be parallel to the incline. While looking at this diagram then, this is the force that is pulling down the hill, right? And so in this particular diagram, f of g after this point is no longer going to be used, right? Because all we care about is the frame of reference vectors, right? Using positive x and positive y. So we're going to resolve f of g into f of g in the x direction and f of g in the y direction, and use those for the rest of the analysis, because what we will find is that a box like this, obviously, as it begins to slide down the hill, depending on the steepness of the hill, it's going to experience friction, which is a resistance to its motion, right? That friction is going to be directed up the hill parallel to the hill, which needs no resolution because it's already parallel to the hill, right? So this would be your f of f value. Friction comes from contact. Contact is defined as normal force. Normal force is a perpendicular contact support force. The normal force is the force that is preventing this box from actually falling to the ground, right? Which is a function of the fact that weight, F of G, is doing in part pulling the box into the incline. So a result of that is that the incline pushes on the box this way, which of course is the contact support force that we call normal force. So again, we know that this is theta, almost always presented in the problems, and through geometry we found that this is theta. So then we can go ahead and resolve f of g into f of gy and f of gx based on this right triangle. But furthermore, we can analyze the fact that at equilibrium, this box does not go along this direction, positive y, or this direction, negative y. The acceleration is 0. So if we did a summation of the forces in the y direction, we know that that is equal to 0 because the acceleration is equal to 0. And so in this case, that means that f of n as a positive value going up minus f of gy in the negative direction is the summation of all the forces in this new reference frame. So setting equal to 0, that means that magnitude-wise, f of n is equal to f of gy in total amount, which should make complete sense, just like it did when the boxes were flat on the ground. The normal force supporting up is balancing out the weight force pulling in the negative y direction. The difference is now that that weight force is not all of the weight force. Only some of it is pulling into the incline. Some of it is pulling down the incline, which means that at a low enough coefficient of friction or a high enough angle, it's possible that this f of gx is bigger than f of f, and this box will slide down the hill, right? And so we have to do the analysis for both the y direction and the x direction. When we do it in the x direction, this is not equal to 0, not necessarily, right? And it would potentially have an acceleration that would either be, well, that would most likely be down the hill, right? So in this case, we have f of gx as a positive going down the hill minus f of f as a negative directed up the hill. As we saw before, the calculation for f of f comes from the normal force, f of f equals mu times f of n. And now, because of this, we know what f of n is, right? And so this is a way to put it all together and determine the actual acceleration down the hill. It's highly advisable that you practice drawing this picture, right? Draw it a few times, make sure you understand what you're doing. Try and flip the incline so that it's sloped the other direction, just so that you can do it from both options. All right. Second theory is a banked angle turn. This is having to do with circular motion. As a car goes around a turn in a road, say the car is facing this direction, these are the headlights, right? From above, in the aerial view, as this goes around the turn, the centripetal force is directed towards the center of the circle, right? The centripetal force being this way, FC. At first, it's not abundantly obvious, but what force is actually creating the centripetal force that is causing this car to make the turn. Friction, correct. If there was no friction, you wouldn't be able to turn. So this is actually F of F, right? We can figure that out if we take the same car and look at it from a head-on view. So if I redraw the car here, where the ground is here, we know that the weight force F of G is down. The normal force F of N is up. These two things are perpendicular to this, right? They are up and down, not left and right from the perspective of the driver, which means they are not the forces that are causing you to turn. The force that is causing you to turn is the friction directed inward on this path, right? So these two diagrams represent the exact same scenario. Through this, we can calculate F of F because we understand the equilibrium component of F of N and F of G here. So it's exactly the same as what we just talked about. This only holds true when the ground is flat, right? But being from Richmond, I'm sure all of you have at least been to RIR at least once. Yes? Never been to RIR? Oh, gotta go. It's so loud, and they usually crash. The raceways, all racetracks, are built where the actual turns are on an incline, right? And the reason for that is very abundant. The faster I go, the higher this friction force must be. And there is a limit that is well below typical raceway speeds, which means that you can't have a flat track and go 200 miles an hour and expect to be able to make the turn and go all the way around, right? So there is not enough friction at those speeds to hold your momentum on the track, right? And anybody that has ever slid out in a turn driving their car has experienced this, right? If you hit a patch of ice or snow or water or whatever, right, gravel, and you slide out, that's because your momentum based on your velocity is directed tangent to the path. And if this force does not change your direction, then you'll continue in the direction of your momentum and slide off of the road, right? Racing would be really boring because no one would be able to make the turns. And so they bank the turns. So if we take this picture and we put the car on an incline, it is hard to draw. So I've taken this road here, and from the inside edge, I've lifted it into the air, and I've drawn the same similar diagram that I had up here, now on an angle. Now I've made it pretty dramatic in this particular diagram so we can see the vectors, but any amount would work. So now when we look at this, right, we know that F of G is still down. But we have to remember, right, being on the incline now towards the center of this circle is still straight out from the car towards the center of the circle. It is not down the hill here, right? It's not down the hill. The center of the circle is over here somewhere, right? Wherever. Because now all it is it's just elevated into the air, but it's still going around a horizontal circle that we have to envision that is there, right? Which means that the centripetal force, the center of the circle, is over here somewhere. I'm just drawing that for reference. So rather than resolving into our inclines that we just had, right, we're going to leave this because we want to look at it as centripetal force. And if the centripetal force is this direction, this weight force is perpendicular to that, we should probably just leave that alone. Because if we change the directions of this, that's going to skew things to not line up with those vectors. So what's important, though, is that the normal force, F of n, directed out like this, the normal force doesn't really match. So we're going to stick to our traditional frame. And rather than resolving f of g into components that match the incline, we're going to resolve f of n into components that match this, your typical frame. We're doing this because we want to see the fact that this can be derived into vectors that are pointing towards the center of the circle and perpendicular to the center of the circle, like the weight force. So we've got one force that is horizontal and one force that is vertical. They are perpendicular to one another, right? And they match up to this frame, right? And so I left f of g alone, and now I'm going to analyze the same summation of the forces in the vertical and the x direction, only now I'm looking at it as straight up and down and left and right. In the straight up and down directions, right, f of n in this direction, f of ny, is pointing up, and f of g is pointing down. Right? And so now we can see that this normal force is supporting the weight. All of it. Right? Because the car is not moving this direction or that direction. Right? It's not accelerating in the vertical or the y plane. Furthermore, this f of n in the x direction is now pointing towards the center of the circle, which means that that can be a centripetal force. That's valuable because that means that there is an ideal angle where f of nx takes care of all of the centripetal force, and therefore friction is not necessary. So on a banked turn, there is an idealized angle where at a particular speed, based on v squared over r, we can get a particular centripetal acceleration that depends on the radius of the curve. In that case, at the ideal angle, there is no need for friction in order for this thing to make the turn. Right? So we can dramatically reduce the necessary friction and allow for an increase in speed and still make the turn. And the example is to think about it on the most extreme case. Right? If I turned this to where the incline is at 90 degrees, right? If the incline is at 90 degrees, then the car looks ridiculous. Set up here like this. But if this is a curve, right, a rounded curve, and I'm just looking at it at a snapshot on the outermost edge of that curve, then at this particular point, the normal force is pointing exactly towards the center of the circle and is doing entirely, right, the centripetal force that's making it go in a circle, which means that if this were possible, you could go at an infinite speed as long as the track can support the weight necessary to push with that normal force. You can go at any speed and you will make the turn. And you've all seen this if you've ever been to any fair where you rode a ride where you stuck to the wall and either the wall went up or the floor went down and you were suspended in the air above the ground spinning. The normal force has become so great that it doesn't matter how fast you spin, because of the fact that it's pointed towards the center of the circle, you are going to maintain your spin, right? But in this case, then we have to consider the fact that now the friction is actually up, because that is what's supporting you against your weight, because your weight is always down, right? So this is a pretty common thing, because if you've ever seen Ripley's Believe It or Not, or one of those shows where they do crazy things with dirt bikes, have you seen the Sphere of Death, where the three guys on dirt bikes go inside the sphere?
Oh, I don't like that. That's really fast.
And then they go really fast. They can go anywhere, horizontal, vertical, diagonal, anywhere, because the curvature causes the normal force to push in. They're not using friction in order to do those loops. They're using the fact that the structure is pushing towards the center no matter what direction they drive. So they can go literally at almost any speed as long as it's adequate to go around the vertical loop, which we've already discussed. Does that make sense? So it's just a couple different ways of resolving these vectors into appropriate directions to match whatever it is that you're trying to analyze, right? If we're trying to look at the acceleration and the weight, it makes sense to match up to the physical dimensions and directions of some of the other characteristics like velocity. But if we're trying to match up with centripetal force, because of the fact that being elevated changes nothing, it makes more sense to resolve the diagonal components into our typical frame that we're already accustomed to, right? And in some cases, you may have to try both to try and make sense of what's happening, right? Because then, to go back to this one, the added challenge then is to figure out what the heck is going on with the friction in this case, right? Because in this case, the friction has to be up the hill or down the hill, right? And it's not abundantly clear which direction that is. If I go too fast, right, to overcome the acceleration that's necessary here, then I start to expand my circle in order to balance that need, which means that this car would attempt to move up the incline and therefore experience a friction that would be this direction. If I go too slow, right, I'm on a hill, which means that I could potentially start sliding down the hill, which would mean that the friction does the exact opposite and pulls up the hill. And again, F of F is dependent on the normal force, and the normal force is this diagonal hypotenuse, right? And so if we're trying to match up to this frame of reference, then we're taking each of these and resolving into components that match to effectively work out those summations that we already addressed. It's an added layer of difficulty, but it's not that much more challenging than any of the other things. Questions? Mara?
How do you find theta for the normal force?
Yes. So through some trig or geometry, I guess, if you like, if I put a more simplified diagram down here, this is theta, and I've got f of n going out like that, right? And I've broken it into this and going up. This and this are alternate interior angles, right? Because this is parallel to that, which makes this 90 minus theta, which makes this theta. So you just have to use some of your geometry that you're used to map it around. If I drew this vertically, it would be the other side, right? Do this one more time. This is theta. Your normal force is here. Sorry. If I did it where I resolved it as in vertical and to the right, then this is theta.